Okay, so now as a couple of examples I'll go through these examples over here, whichever one is really important. We will talk about them here and then let's see where that takes us. So for example, let's say that you have x plus 1 comma y minus 2. This is an ordered pair, and that is equal to 3 comma 1, for example. 3 comma 1. And we said that an ordered pair, basically two ordered pairs are equal if the corresponding elements in that ordered pair are equal. Meaning that since the two ordered pairs are equal, the corresponding elements then must be equal. Meaning that x plus 1 must be equal to 3 and y minus 2 must be equal to 1. And that means that x is equal to 3 minus 1, which is equal to 2, and y is equal to 1 plus 2 is equal to 3. And now suppose that, for example, as another example, suppose that you have basically two sets, for example, P, capital P, which is, for example, A, B, and C, and you have another set Q, which is equal to only one element R. And if you want to form the two, basically the two Cartesian products of these two sets, meaning P times Q and Q times P. The way to calculate that, of course, you know that P times Q is going to be equal to basically all the ordered pairs that you can form using the elements of these two sets. But when you have P times Q, first you have to take basically the first element you have to take it from P, meaning that you will get, for example, A comma R, B comma R, and C comma R. That is P times Q. And then basically if you want to calculate Q times P, then you have to take your first element from the set Q, meaning that you need to write this as R comma A, R comma B, and R comma C. So you have R comma A, R comma B, and R comma C. So that is basically, for example, the two different Cartesian products that you can get using these two sets. And of course over here you can of course see that by the definition of equality of ordered pairs, we said that, for example, A comma R is not the same thing as R comma A, and of course B comma R is not the same thing as B comma R, or C comma R is not the same thing as R comma C. So then of course you can conclude that P times Q is not equal to Q times P. Okay. But of course the number of elements in these sets are equal. Now if you basically like to work a little bit using the notation of sets, for example, B intersection C, B union C, and that sort of thing, here is a good example. So for example, let's say that you have set A is equal to, for example, 1, 2, and 3. let's say that, for example, the set B is equal to 3, 4, and the set C is equal to, for example, 4, 5, and 6. Now, if you want to, suppose that you want to calculate, for example, the Cartesian product of A and B intersection C, and B intersection C. Now, in order to calculate that, first you need to calculate B intersection C. So B intersection C is basically the set of all elements that are common between B and C, which is basically only 4. So now B intersection C is 4 and A is basically 1, 2, and 3. And now the Cartesian product of A and this set over here is basically this set over here, this set of ordered pairs, and then first you need to take the first element from this set A. So you have 1, 4, you have 2, 4, and you have 3, 4. That is basically that. Now, in the same situation, for example, if you want to calculate the Cartesian product of A and B intersection with the Cartesian product of A and C, so the Cartesian product of A and B would be basically, the Cartesian product of A and B would be basically a set over here, which is, first you need to take your first element from the set A. So you have 1, 3, you have 1, 4, you have 2, 3, you have 2, 4, you have 3, 3, you have 3, 4. Okay, and that's the Cartesian product of A and B. Now the Cartesian product of A and C is equal to a similar set to this set, but of course the elements are going to be different. So take your first element from A and C. So 1, 4, 1, 5, 1, 6, 1, 4, 1, 5, and 1, 6, and then you have 2, 4, 2, 5, 2, 6, 2, 4, 2, 5, and 2, 6, and then you have 3, 4, 3, 4, 3, 5, and 3, 6. Now the intersection of these two sets, now this is A times B, or the Cartesian product of A and B. This is the Cartesian product of A and C. So A times B intersection with A times C is basically the set of all ordered pairs which are common between these two sets. So for example, here you have 1, 3 that you cannot find here. 1, 4 you can't find it there. 2, 3 you cannot find it there. 2, 4 it is there. 2, 3 is not there. 3, 4 is there. So that's only these 3 elements. So 1, 4, and then you have 2, 4, and then you have 3, 4. So that's basically that, for example. Or suppose that you want to calculate, for example, another part of the same thing. You want to calculate for example, the Cartesian product of A and B union C. So first I calculate B union C, and then we'll see about the rest of the things. So B union C is a set of elements which is 3. So basically it's going to be a set that contains all the elements of the elements on B and the elements of C, but nothing is supposed to be repeated. Meaning that, for example, you can see that 4 is common between these two sets. So I don't write 4 twice. I just write it once. 3, 4, 5, and 6. Now the Cartesian product of A and B union C is basically the Cartesian product of this set and this set over here. And that's going to be equal to, basically, you take your first element from here. So this is 1, 3, 1, 4, 5, 6, 1, 4, 1, 5, 1, 6, and then you have, you have 2, 3, 4, 5, 6, 2, 3, 2, 4, 2, 5, 2, 6, and then you have 3, 3, 4, 5, 6, 3, 3, 3, 4, 3, 5, and 3, 6. That is basically the answer to this part. 1, 3, 1, 4, 1, 5, 1, 6, 2, 3, 4, 5, 6, 3, 3, 4, 5, 6, and so on and so forth. Now suppose that you want to calculate the Cartesian product of A and B union with the Cartesian product of A and C. So in order to calculate that, first I need to calculate these two parts. So to calculate these two parts, so first the Cartesian product of A and B is basically the Cartesian product of these two sets, which is 1, 3, 1, 4, and then you have 2, 3, 2, 4, 3, 3, and 3, 4, 3, 4. So you have 3 times 2 is equal to 6, basically 1, 2, 3. So that is that. So that's the Cartesian product of A and B. Now the Cartesian product of A and C, is going to be equal to the Cartesian product of these two sets. So you will get 9 pairs over there. So you have 1, 4, 1, 5, 1, 6, you have 2, 4, 2, 5, 2, 6, and you have 3, 4, 3, 4, 3, 5, and 3, 6. That's the Cartesian product of A and C. Now if you take the union of these two sets, you're going to need to write all the ordered pairs that there are in this set and also in this set, but then you cannot repeat anything. No repetition is allowed. So then A times B union with A times C is going to be equal to, so I write 1, 3, 1, 4, 1, 3, 1, 4, and so these two are taken care of, and I have 1, 5, I have 1, 5, 1, 6, and I have, so these are taken care of. So I have 2, 3, 2, 4, 2, 5, 2, 6, 2, 3, 2, 4, 2, 5, 2, 6. So this is taken care of. And I have 3, 3, 3, 3, 3, 4, 3, 5, and 3, 6. 3, 5, and 3, 6. And that's all the elements of this set over here. So that was basically an example using the notation of the concept of union and intersection and all of those things. So that's basically one thing over here. Or okay, so now as another example. Let's suppose that you have this is just to get a little bit more familiar with the concept. So the question is, if R is the set of all real numbers, what do the Cartesian product R times R and R times R times R represent? So suppose that R is the set of all real numbers. Then the Cartesian product R times R, this would represent the set R times R. This would represent the set R times R, which would be basically this set over here would be equal to the set of all ordered pairs x, y, such that x and y belong to R. Okay, which represents basically the coordinates of all the points in two-dimensional space, which represents the coordinates of all the points, in two-dimensional space. And R times R times R would be the set, represents the set basically that all the ordered triplets x, y, z, such that x and y and z belong to the set of real numbers, which represents the coordinates of all the points of all the points in three-dimensional space. In three-dimensional space. Okay, so that is that. Now there is, let me take a look at these examples and see if there is anything important here. There's anything important here. Now as another example, so for example, let's say that you have some set A. Set A, for example, A has 3 elements, and set B is equal to 3, 4, and 5. 3, 4, and 5. Find the number of elements in A times B. You want to find the number of elements of A times B. So we said that if the number of elements in set A is basically P, and if the number of elements in set B is Q, then the number of elements of the set A times B, which is the Cartesian product of the two sets, is going to be P times Q, which is in this case is basically 3 times 3, which is equal to 9 elements. So that's basically that. And that is that. Or suppose that, for example, you want to say whether these statements are true or false. Let me create a new layer over here. So for example, it says that basically if P is equal to, if the set P is equal to M comma N, and the set Q is equal to, for example, N comma M, basically the exact same elements in a different order. Of course, that doesn't make any difference. Basically, they are basically the same sets. Then P times Q is going to be basically M comma N and M comma M, and then you have N comma N and N comma M and N comma M. So that's basically the elements of that set. Now let me basically find the answers over here to check my answer. So this answer is actually correct. And for example, another question is if A and B are non-empty sets. A and B are non-empty sets. Then A times B is a non-empty set of ordered pairs X and Y such that X belongs to A and Y belongs to B. If A and B are non-empty sets, then A times B is a non-empty set, is a non-empty set of ordered pairs X and X comma Y such that x belongs to A and y belongs to B, which is of course true. This is true. The third part of this question is if A is equal to 5, which is the empty set. No, I'm sorry. If A is equal to 1, 2, and B is equal to 3, 4, then A times B intersection with phi is equal to phi. Okay, so the intersection of any set with the null set is of course the null set, and then now suppose that this is the null set, and of course then if you have the Cartesian product of any set with the null set, it's going to be in the null set. So this is true. So number 4 is true. It doesn't really matter what A and B are, since basically this statement basically applies to any A and B really. And there is another good question over here. So suppose that you have A times B. The Cartesian product of A and B is A comma X, A comma X, A comma Y, and B comma X, B comma Y. And so you want to find A and B. Find A and B. So basically since you have A times B, what this means is that basically all of these first elements come from A, of course. So then you can say A is equal to basically A comma B, A and B. And all of these second elements come from B basically. So then you can write B is equal to, for example, X comma Y, X comma Y. And that is, and of course if you calculate A times A, the Cartesian product of the two sets, you would get A comma X, A comma Y, B comma X, and B comma Y, which is basically the same thing that you have over here. So these are the two sets that you have. And then there is a couple more things over here.